Welcome back. Today we're going to be looking at section 5.6, which is about rational functions. This is going to feel a lot like when we did dividing polynomials. We're just going to be looking at what they look like on graphs and how they behave. So let's go ahead and jump right in. Today, instead of our scripture or daily scripture, we have a quote by C.S. Lewis, who's my favorite. Maybe C.S. Lewis, attributed to C.S. Lewis. And it's just a reminder that I know the past few videos, if you've learned 5.4, 5.5, and now 5.6, have felt really tedious and like we're doing a lot of work. And that's true, we are. We're getting into a part of college algebra that's tough for a lot of students. But a reminder as to why we're doing this and where our value and where our worth come from. Lewis said, "Education without values, as useful as it is, seems rather to make a man a more clever devil." And so the idea is, as we move forward in learning these really useful skills for not just your math future, but all learning that you're going to do, whether it's in the engineering field or the sciences field, or just for your own self-improvement, that not to forsake our values in the process, and that our own integrity and our own character is worth preserving in the midst of doing all these things. So just a little charge against cheating, I suppose. Stay away from photo math. And remember your integrity and your character and your values as you're becoming educated. So today we're going to talk about rational functions, and we're going to talk about what they look like on a graph and how they're manipulated. And so I'm going to give you the two toolkit rational functions, which we've talked about a lot in a lot of these videos if you've watched through them all, and saying, please, please know these. You'll notice this one's the 1 over x, and this one is 1 over x squared. So this one is called the reciprocal function on the left, and this is the reciprocal squared function on the right. And that's what they look like. So as we shift them up, shift them over, and move them around, it's important to know kind of what they are. Okay. So what we're going to do first is we're going to define vertical and horizontal asymptotes. Vertical asymptotes are these dotted lines where x is not allowed to exist. And you'll notice that there's no blue line crossing that vertical dotted line. So that's a vertical asymptote, which is a part of the graph where the function tends towards infinity at the top or negative infinity at the bottom as x approaches a value from the left to the right. A horizontal asymptote is saying as x goes towards infinity, our graph or our y value approaches a number, in this case 0. And so the horizontal asymptote, even though it's not on that graph, would occur right there at the origin or on the x-axis. Okay, and we're going to learn how to find these today. But the first thing we're going to do is just describe them. And so it says, use arrow notation to describe the end behavior and local behavior for the reciprocal squared function. Like I said, that was one of the toolkit functions to memorize, and that function looked like this. And so what I'm going to do is one step at a time, look at each of those arrows and decide what arrow notation to give it. So I'll start with the far left, and I'll say this arrow says as x approaches negative infinity, because that's where the x value is getting smaller and smaller and smaller. What does y do? Well, the y value, or the value on the y-axis, gets really close to 0. And so that's the red arrow. And I'm going to flip it around and go towards the right end and say as x approaches infinity, you'll see that y also approaches 0. Y gets really, really close to 0 as x gets really, really big. And then at the top, on the right here, we're going to use a little trickier notation and say what number is x getting really close to, because it's not infinity anymore. We're saying as x gets really close to 0 from the right side. So we put a 0 plus to say from the positive side, as x gets close to 0 from the right side, y gets really, really close to infinity, or tends towards infinity. And then lastly, at top here, as x gets really, really close to 0, but from the left side, or from the negative side of it, y tends towards positive infinity again. And so there's arrow notation to describe the end behavior and the local behavior. And we looked at those 4 arrows to kind of know what this function's doing at those places. Cool? Let's move on. So now we're going to sketch the graph of the reciprocal squared function, so that same function, but we're going to shift it to the right 3 and down 4. And so what I'm going to do is I'm going to give you those asymptotes to start. We've got the vertical and horizontal asymptote of the reciprocal squared function. Remember, the reciprocal squared function is f of x equals 1 over x squared. And if you wanted to plug and chug a few points, the only nice points that you can really plug in that are pretty numbers are 1 and -1. And the functions kind of look like that going on forever. If you go back and look at the toolkit functions you need to know, you can see those points being the only points that are real nice, pretty numbers. Everything else is real fractions or just a giant number. All right. Now we need to shift it to the right by 3. So what I'm going to do is I'm going to take that vertical asymptote as the starting point and shift it to the right by 3. It's easy to start with that vertical asymptote because it kind of governs your entire function. And then we need to shift it down by 4. So what I'm going to do is I'm going to take that horizontal asymptote and I'm going to shift it down by 4. So make it orange, and shift it down 4. And there's my new point of reference for my function. So it used to be up there at the top, got shifted down and to the right. And instead of using the points, I used the asymptotes to do it. So we went down 4, -4, and we went to the right 3, which was a +3 to the right. And then I'm just going to graph that function again. Say, okay, well, my points were up 1 over 1 from the origin and up 1 over 1 for the origin. So my new function should look something like that. And using the properties of transformations of functions, we could write this equation actually. We don't have a ton of room to do it, but maybe right underneath the function I could say h of x equals 1 over, and if you remember, inside of the function we get the horizontal shift. So if it's to the right by 3, we should get x -3 because it's opposite of the direction you went. And if it's down by 4, we should get -4 on the outside. And so there's my shifted reciprocal squared function, the -3 and the down 4. And I didn't even plug in a number. That XY chart is there if you need to use it, but we didn't plug and chug any numbers. We were able to figure out what this function should be on its own. All right. So now we're actually going to look at rational functions and what they are. If you look at this really long equation, all this is a polynomial on top of another polynomial. A really long equation on top of another really long equation. And for the sake of time, I'm going to skip down here and start looking at the domain. I'm going to skip try it 3 and let you try it on your own, maybe after you've watched the rest of the video, so we can get back to, so you can kind of experience what these things feel like before applying a word problem to them. But I would encourage you to try this on your own, and you can look at the notes and the completed notes to fill it out. But I would suggest doing that after we've completed all of the notes so you have a little bit of practice with these equations first. So here we go. We're just going to talk about domain of rationals. It's the exact same as domain before. So if you remember that domain chart where we talked about the 2 conditions that the domain can't be, we said the denominator cannot equal 0, and we said the inside of a square root has to be greater than or equal to 0. Those were the 2 conditions we gave. Well, here we just have a denominator, right? We don't even have any square roots. So the only thing we need to do is say the denominator can't equal 0. And so what I'm going to do is I'm going to take that entire denominator off to the side, and I'm going to say you are not allowed to be 0. And then using the factors, we're going to split it up just like we factor normal things that do equal 0, but say, hey, x, you're not allowed to be 1, and x, you're not allowed to be 5. And so what does that look like on a number line? That looks like 1 and 5 being the not allowed numbers and every other number in the world being allowed. And so then our final answer usually goes in interval notation. So we say we start as far as we can at negative infinity, and at 1 we skip over 1, we We walk to 5, we skip over 5, and we walk to infinity. And so there's our domain in interval notation. And that is not a new property. That's a property left over from the domain section, just applied to a new type of function. We're going to talk about what those things are in a second, what those discontinuities or those domain restrictions or those errors are in a second, but that is just how you find domain. All right, here's a chance to talk about vertical asymptotes and removable discontinuities, also known as removable holes. Sometimes you'll see it written as that. And so what I'm going to do first, before even explaining what each one is I'm going to factor this, because this looks like a factorable thing. So I'm going to say I'm going to use perfect squares to factor the top, x plus 5, x minus 5. And then I think I'm going to have to do this in 2 steps, unless you can see it right away. I'm going to say the bottom, I'm going to take out an x from the whole thing, and I'm going to be left with x squared minus 6x plus 5. And then I'm probably going to go one more step and say, okay, well, are there properties of 5 or factors of 5 that add up to get you negative 6? There are. So I'm going to say x plus 5 on the top, x minus 5 on the top, x on the bottom, x minus 5 on the bottom, and x minus 1 on the bottom. And so that would be like a fully factored version of this rational equation. Rational because it has an x on the bottom and the top. Fully factored because you can see all of the factors in parentheses by themselves. All right, and because we have all those factors, we can finally define our terms. So here's what we're going to do. The first thing I'm going to do is notice something in common on the bottom and the top that's going to slash out. And that's where the word removable is going to come from. So if you can cancel a term like that, so if you can cancel, that's where the word removable, because you kind of removed it. Removable hole. And where is that removable hole at? Well, it's when you plug and chug 5, you get a 0 on the bottom, and that would be bad. And so the removable hole occurs at x equals 5. If you can't cancel, but you still have 2 terms on the bottom, these ones boxed in red, then we're going to set each of those equal to 0 separately and say x equals 0 for the first term and x equals 1 for the second term are vertical asymptotes. And so what we have is 3 places on our graph where if we were to plug and chug those numbers, something bad would happen. Something bad from the 4th grade would happen, which is dividing by 0. And so from those 3 things, we can kind of draw a conclusion that how do we find vertical asymptotes or removable holes? We set the bottom equal to 0. So setting the bottom equal to 0 is the way that we found all of those bad numbers or domain restrictions. So if we set the bottom equal to 0, we can find 3 of those bad numbers. And so then we're going to do one more step with this blue removable hole term to say, actually, not only can we find where the removable hole exists, but we can find what it is. And so what we're going to do is we're going to take our factored form, except for the term that was removed, and say, I'm not going to call it f of x because it's not the same function, so I'm going to call it like h of x equals that term once the hole has been removed. And what I'm going to do is I'm just going to plug and chug that location. And so h of 5 equals 10 over 5 times 4, which is just 10 over 20, which is 1/2. And so where is my removable hole actually at? The removable hole is at 5 comma 1/2. And what does that look like on a graph? Well, it looks like the normal function is just existing, but it keeps going. And so unlike an asymptote, a removable whole looks like the normal function, it's just missing a spot. What is a vertical asymptote? To remind you from that other section, a vertical asymptote looks like a vertical line that the function was not allowed to touch and approached infinity or negative infinity at a spot. Okay, so rule number 1, and an important rule, setting the bottom equal to 0 gives you wholes or asymptotes. Rule number 2, horizontal asymptotes. How do you find them? Well, there's like a 3-part system to find horizontal asymptotes. So here's what you're going to do. You're going to get the leading terms. And you're going to get the top over the bottom leading term. So you're going to say leading term of the top over the leading term of the bottom. And we're going to look at that and analyze that. And and it's going to break into 3 things that we're going to have to memorize. There's 3 bullets up there if you want to go and look at the book's definition of these. But I'm going to give you the shorthand version of it. So you take the leading term of the top, you take the leading term of the bottom, and you look at the degree. And if the top is bigger, then it's none or a slant. If the degree is the same, then it's y equals a over b, where a over b are your coefficients from the leading term. And if the bottom is bigger, it's literally just y equals 0 every time. So those are your 3 possible answers. None or a slant. And we'll talk more about slant asymptotes. If you move on to pre-calculus, we'll find the actual slanted line that is an asymptote. But for this class, you're just going to say none or slant. And so here's what we're going to have to do is we're going to have to find that leading term. But I'm going to find it without factoring and foiling the whole thing. Well, okay, we can just factor as practice or foil the entire thing. So if we foil the top, we get 4x squared plus outside 2x, inside minus 2x, last negative 1. And if we foil the bottom, we get x squared, outside plus 3x, inside minus 2x, last negative 6. How did we do that? We foiled. If you need practice foiling, please go back and watch some of the videos from chapter 2. We practiced foiling a lot in chapter 2, and now we're having to move a little faster so we're not explaining it every single time. All right, let's reduce that a little bit and say this is just 4x squared minus 1 over x squared plus x minus 6. Okay? And so we got that. We got the leading terms I'm going to highlight. Boom, boom. Those are the leading terms. And so using those leading terms, we're going to look at the degrees. And the degrees are the same. And so the horizontal asymptote is just y equals 4 over 1. Where we took the coefficients of 4 and we took the invisible coefficient that's hanging out right there of 1 and we put it over each other because it was the same using that 3-part system there. If the top was bigger, we would have had a different answer. If the bottom degree was bigger, we would have had a different answer. But because the degrees were the same, we just divided the coefficients. This problem also asked us for vertical asymptotes. So we'll do that off to the other side. We'll do it in green. It asked us for vertical asymptotes. And remember, that was just setting the bottom equal to 0. And so we're just going to take x cannot be 2. That would be bad. And x cannot be negative 3. And that came from bottom equals 0 or denominator equals 0, and making sure that nothing canceled. If you look at these, none of these terms cancel with the terms on the top, And so there's no removable holes. So we've got our vertical asymptotes, which we learned in the last try it problem, and we've got our horizontal asymptote, which we just talked about. All right, intercepts, they're exactly the same as before. So finding the intercepts is like before. I'm going to give you the easy one first, which is find the y-intercept. And if you remember from all the other videos, how do you find the y-intercept? You just plug and chug 0. And so if you plug and chug 0 into this equation, you're going to get -2 on the top, +3 on the top, over -1, 2, and -5 on the bottom. And then we need to reduce all of those terms. And so that's just going to be -6 over a +10, which is divide by 2 on the top and the bottom. You get -3 over 5. And so what was our y-intercept? 0, -3 over 5. Y-intercept, I think, is the easier one. You just plug and chug. For x-intercepts, in the past, we've said you set the whole thing equal to 0. And that's still true. But I'm going to give you a little hint or a little shorter way to do it. We're just going to set the top equal to 0. Because if the bottom was set equal to 0, or if the bottom was included still, we could just take the whole bottom and multiply it over, and 0 times anything is 0. So we're just going to take the top and set it equal to 0 for the x-intercepts. So x minus 2, x plus 3 equals 0, and that is already factored for you, so you can jump straight to writing x equals 2 and x equals -3, which means your intercepts are 2, 0 and -3, 0. And there's your x-intercepts. So x-intercepts and y-intercepts are the same as before, where we plug in 0 or we set equal to 0. Nothing's changed about those. All right, try it 3. It's going to feel a lot like one you've run before, where you're shifting a reciprocal squared function to the right 3 and down 4. I'm going to let you try that on your own so that we can get to the last problem of this section, which is going to take a little bit of time, but it's going to review the whole section in one. So here's the last problem of this section, where it gives you a rational function, and it just says, hey, graph this thing. And I'm going to give you all the tools you need to graph it in this one problem. So here we go. We're going to start with what I think is probably the easiest thing to find, the y-intercept. So if we made like a 4-part system, there's 4 different things we can find. The first one is the y-intercept. And how do you find the y-intercept? You plug in 0. So f of 0 is just going to equal, I might need to make this bigger. Let's look. It's going to be 2 squared on the top, -2 on the top, 2 on the bottom, -1 squared on the bottom, and -3 on the bottom. All we did is we plugged in 0 everywhere we saw an x. That's just plug and chugging 0. And so if we work that out, we get 4 times -2 is -8. And this is going to be a 1 right there, because -1 squared is 1. So it's going to be over -6. And that's just going to be 4 over 3. And so our y-intercept is 0, 4 over 3. We've done one of the 4 things. Like I said, I'm going to divide this into like a 4-part problem with the 4 things we've learned today. And I think y-intercept's the easiest, so go ahead and get that on the graph. You might have to zoom in. 4/3 is like about right there, so I'm just going to put a point there for my y-intercept. All right, next up, I'm going to find my vertical asymptotes. Sometimes we'll write VA as an abbreviation. If you remember how we found the vertical asymptotes, we set the bottom equal to 0. And so there's the bottom equation right there. 2 parentheses x minus 1 squared times x minus 3 equals 0. And if we factor this, and we look at the factors and the zeros they result in, we get x equals 1 with the multiplicity of 2, and x equals 3 with the multiplicity of 1. And so those are my vertical asymptotes. And so I'm just going to plot the lines x equals 1 on the vertically and x equals 3 vertically. And now I've got two vertical asymptotes from this function that I know about. And I know their multiplicities, which is kind of going to help me solve this problem. All right. Next thing we're going to do is we're going to graph, or we're going to solve for the x-intercepts, which is going to feel a lot like vertical asymptotes. So the x-intercepts we'll do in green, and we'll take, and if you remember the x-intercepts, we said it's going to take the top and set it equal to 0. So we got x plus 2 squared and x minus 2 equals 0. And we're going to solve those two things almost the same way we did before, where we're going to say this is negative 2 with a multiplicity of 2, x equals, and this is x equals 2 with a multiplicity of an invisible 1 right there. And so I can go and put two x-intercepts at the points, I'll make them green, negative 2, that's going to have a multiplicity of 2, and at x equals 2, and that's going to have a multiplicity of 1, meaning it's going to cross. All right, next thing we're going to do is we're going to hunt down the horizontal asymptote. And to do that, we're going to look at our leading terms. I might stay up here for this. I know I was going to do it down there, but I might stay up here because it'll be a little easier to see. The horizontal asymptote, I'm just going to look at all of the leading terms. So I see a 2 right there. I see an invisible 1 right there. And the degrees. So I see a degree of 2x's right here and 1x right there. So the degree on the top is 3. And I see 2x's right there and 1x right there. So the degree on the bottom is 3. And because those degrees match, our horizontal asymptote is just y equals the coefficients in the front, 1/2. And so I can draw a horizontal line at y equals 1/2. I'll make that purple. Draw a horizontal line and move it to right at 1/2. And already with those 2 points and that horizontal asymptote, I can see the left side of this equation and what happens. These 2 points have to attach to one another. And because there's no other x-intercepts right here, I can't turn around and go down because then I'd have an x-intercept that we would have already calculated. And so it has to go up. And this side, we already said the horizontal asymptotes mean it approaches that purple line as x goes to negative infinity. And so it has to approach that purple line. The next thing I'm going to do is I think I'm going to plug and chug a point just to kind of feel it out. Well, it's a pretty ugly equation. Maybe we won't do that. Maybe we'll look at the multiplicities of our vertical asymptotes. So if we go down and look at our vertical asymptote, the one that occurred at x equals 1 had a multiplicity of 2. So this one had a multiplicity of 2, and the other had a multiplicity of 1. And if you think about multiplicities, just like they were with the x-intercept, or the x-intercept on the x-axis, if it was even, it bounced off the axis. And if it was odd, it crossed the axis. Well, asymptotes work the same way. If it's even, so this first one has a multiplicity of 2, which means it's even, it's not going to bounce off the axis because it's not approaching the axis. It's going to like bounce off of infinity and come back down. So instead of bouncing off the axis, which is at 0, it like bounced off infinity and came back down. It never really reached infinity because it just tended to or approached infinity. But you can kind of imagine it bouncing off that asymptote and coming back down. And because there's no other x-intercept, this has to keep going all the way through and go down. And does that check out with our multiplicity of the x-intercept? So this should have a multiplicity of 1, and this should have a multiplicity of 2 if it bounces. Let's go look and see. We didn't even check that earlier, but our graph would have spoken to it. If you look at the bottom there, our x-intercept at negative 2 had a multiplicity of 2, which means it needed to bounce off of negative 2, and it did. And our x-intercept at 2 has a multiplicity of 1, which means it needed to cross, which it did. So our x-intercept multiplicities worked too. Now let's look at the multiplicity in air quotes, because it's not called a multiplicity, that's 4 zeros, but it's like the multiplicity of the asymptote if you're trying to graph these functions. It behaves in a lot the same way. Because we have an odd multiplicity here, we're going to cross the x-axis. So it was down here. When it hits that asymptote, it has to cross the x-axis and approach from the other side. And we're going to approach that purple asymptote as we go towards infinity. And it makes sense to us that that should stay on the top right quadrant of this entire graph because there's no x-intercept over there. So it can't cross down and hit the x-axis. We only had those two green x-intercepts. And so using those 4 skills, using the horizontal asymptote, which I wrote up here, but we could put down in that quadrant now, the y-intercept, the x-intercept, and the vertical asymptotes, we can graph some really ugly functions without ever having to plug and chug a point. The only real point we ever plugged and chugged was 0, 4/3, because we plugged and chugged our y-intercept. But all the other points were just kind of given, or all the other graphs were given to us by features of the graph, which I think is a really impressive thing. If you need to pause that and look at it or re-watch it or re-practice it, I encourage you to do that. Thank you for watching this far, and I'll see you next time.